we continue to discuss manufacturing facilities and related production systems. The latter is a network of interdependent operations resources that work together to transform raw materials into finished goods. The first part of this video presentation examined a simple reference system proposed by James Holt in the JobShop game simulator, with 4 workstations A, B, C, and D, and 4 different end products with different roadmaps. The total touch time is exactly 4 days for each one, but it takes 1 day on B to make yellow or green product and 2 days to make blue or orange. We assume that at the beginning of each business day, 1 customer order was placed for only 1 product, and we took 24 orders with 6 products of each type, arriving in a certain random sequence. Raw materials for all products are supposed to be always available, and the system is empty at the beginning of each simulation session. Using this example, the myth was debunked that in order to improve performance, it is mandatory to load the machines as much as possible and put orders into production as early as possible. On the contrary, DBR technique has been shown to provide maximum performance with later starts and lower overall resource utilization. Let me remind that we called the workstation B a drum, define the work in process buffer R as the total number of days it will take for workstation B to process all orders still in production, denoted R with an asterisk as the length of the rope and set it to 4 days. The ERD rule was used to manage queues, meaning that the order with the earliest release date was selected for processing. And we followed the rule: if at the end of the business day the buffer size exceeds the rope length, the next order in line is not put into production. Under the above circumstances, the system operated at its maximum capacity, stably in terms of the work in process level, and therefore predictably in terms of the production lead time. In fact, a bottleneck-free logistics structure was implemented, with the capacity constraint B as the only control point for the entire system. It was also shown that, given the specified demand structure, the maximum capacity of such a system is 2/3 of the order per day on average. Let's now use the same example to explore 3 other common questions that arise when applying DBR. Namely, what if the demand structure is changed? Can a specific order due date be promised right upon placing the order? And what if the length of the rope is changed? The answer to the first question is quite clear without additional explanations. From the table shown, it obviously follows that for any demand structure in which the share of the second and/or fourth product is greater than 0, resource B remains the only capacity constraint for the system and determines its overall performance. As for the second question, part of the answer has already been given earlier. In a stable system, the production lead time, that is, the time from when the order is put into production, is predictable. In our case, it averages 6.5 days, but does not exceed 9. In other words, we can be quite sure that any order will be completed within 9 days of its release. The only thing left is to estimate the time interval between placing an order and putting it into production. In our system, where the capacity-constrained resource B is not idle, the size of the time buffer R is reduced by 1 at the end of each business day, and to maintain a fixed rope length, the next order can be put into production. Therefore, taking into account the different requirements for B, it is sufficient to calculate the total number of days it will take for workstation B to process all orders still not in production. Let's take a look at the situation at the beginning of the 17th day, for example. There are 4 orders in the queue, requiring a total of 6 days of processing on B. So when the 17th order arrives, its due date can be estimated as 16 plus 6 plus 9. That is the end of the 31st day. In general, for our example, the promised due dates may look like this. And here is how the plan is implemented, including the time spent in production. Answering the third question, let's run 3 more simulation sessions of our system with higher and lower rope lengths. If it's set to 5 instead of 4, here is how the system state changes over time. Well, during the selected reference time frame, when the system is running in full swing, the same 14 orders were completed and the overall machine utilization remained approximately the same. The work in process remained stable at a slightly higher level of 5 instead of 4.5 orders, as did the production lead time, which averaged 7.2 instead of 6.5 days, with no bottlenecks in the system. Moreover, with the same 9-day upper limit for production lead time, the whole orders execution picture also looks pretty much the same. If we now set the rope length to 3 days instead of 4, the system will work as follows. It is still running at maximum capacity, with stable performance, although, as expected, at a lower work in process level, and consequently a shorter average production lead time. There are no bottlenecks either, and given the same 9-day maximum production time, the promised due dates are perfectly adhered to. Comparing the original and the 2 additional scenarios discussed above clearly demonstrates the system's resilience to changes in control parameters. The key point is that the capacity constraint B is the only resource worth worrying about loading. Moreover, from the whole system management perspective, the cycle time for other resources does not really matter, and for the resource B it may only be approximately known. Obviously, however, if the work in process level in the system is significantly reduced, then B may sometimes be idle. Let's set the rope length to just 2 days and look what happens. There is no work for B on the 13th day, nor 18th day, nor 21st day, and so on. As a result, the last order is completed on the 44th day only, instead of the 38th in previous scenarios, which in turn leads to a decrease in the overall system's capacity. So that only 12 orders instead of 14 are now completed within our reference time frame. although the system continues to operate stably at even lower work-in-process level and shorter production lead times. Summarizing the results of the first and second parts of this presentation, let me formulate the following general conclusions. Capacity constraints as attributes of the production system's dynamic complexity are strategic control points for manufacturing facilities. Capacity-constrained job shop manufacturing process can be managed by implementing a logistics structure with a single control point and no bottlenecks. If the capacity constraint is clearly known, the proper logistics structure can be built using the drum buffer rope technique. In this case, the manufacturing is stable, the production lead time is well predictable and robust, as are the customer orders' due dates.